Okay, let me introduce the final speaker today. Liedtke. You still at Stanford University?
Yes.
We'll speak on also special concrete object, Enrique surfaces. It's classification of Enrique surfaces in characteristic especially two.
Especially two, yes. Yeah, thank you very much for giving me the opportunity to talk here. So I've seen that some of the speakers have these nice printouts. Unfortunately, I don't, but everything I'm talking on today is on archive. So let me recall, there is this Enrique's classification of algebraic surfaces, and then, as we all know, we've had just a talk on K-free surfaces, and there are three more classes in Kodaira dimension 0. There is abelian surfaces. There is this highly explicit class of bi-elliptic or hyperelliptic surfaces, and then there are Enrique surfaces. And I should say, I'm starting off with a slightly unusual definition. So what is an Enrique surface? Well, it means for me that the canonical class is numerically trivial and that the second Betti number is equal to 10. So this is kind of the point of view taken by Bombieri and Mumford. When they did this in arbitrary characteristic, and sort of from the classification of surfaces, this is kind of, we will see in a second why this is kind of better than what you might think. So this implies, for example, that chi of Ox is equal to 1, that the first Betti number of x is equal to 0, and it also implies that in fact omega tensor omega is trivial. Well, if the characteristic is not equal to 2, so if we're working over a field of characteristic not equal to 2, then in fact something much more familiar is true, namely, in fact, the canonical class is non-trivial, and having that defines us, we can simply write down the following object. So we can use this to define an algebra structure here, which is finite étale of degree 2 on X. And then it turns out that this X here is a K-free surface. And so let me say a little bit sloppily, so the theory of Enrique's surfaces therefore becomes a subset of the theory of K-free surfaces. So usually the many results on Enrique surfaces are proven by simply passing to the double cover, working there, keeping track of the involution, and then going back. So because of that, in many cases it suffices to prove, it suffices to simply look at the theory of K-free surfaces. Another nice thing is that H2 of theta is 0, which implies that the deformation space is smooth. H1 of theta is 10. So in particular, we know it's 10-dimensional. And over the complex numbers, it's known that the moduli space is, of course, smooth, 10-dimensional. But even more, it's unirational. It's irreducible. That follows, for example, from the Torelli theorems, again, for K-free surfaces. And, for example, by a result of Kondo, it's not only known to be unirational, it's in fact a rational variety. So quite a lot is known. So let's talk a little bit about characteristic 2. Well, then the following happens. First of all, there are 3 types. rather than 1. Namely, the first possibility is that the canonical class is again non-trivial, which implies that h1 of OX equals h2 of OX 0. And these surfaces are called classical. Although, in a certain sense, they are not. Then we have the following possibility. Omega x can be trivial. And then kind of difficult things happen. Then what happens is that h1 OX equals h2 of x is 1. These are the non-classical ones. Because this is one-dimensional, we have an action. We can look at the Frobenius action. So we have OX, we have f equals Frobenius acting on that. And there are two possibilities. I mean, this is a semi-linear map, so it can either be bijective, in which case the surface is called singular. It's not singular in the sense that it's not smooth. It's just a name. And then if it's 0, the surface is called supersingular. And just as a warning, we've heard just in a talk that there is a notion of supersingularity in the sense of Shioda. That is, if rho is equal to B2, with respect to that notion, every Enrica surface in any characteristic is supersingular. So again, this may be not the best, but the terminology goes back to Bombieri and Mumford, and I will not change it. What can we say in this case? So let me draw a couple of observations that show us that the theory really becomes difficult and different in characteristic 2. First of all, singular and classical Enrica surfaces are open in families. Well, for the classical ones, this is clear from semi-continuity and the fact that h1 is 0. For the singular ones, you can play a similar game with h0 of omega, and then h0 of omega is 0 for those, and it's one-dimensional for those and those. So again, by a semi-continuity argument, it's clear that both types are open in families, and that tells us already that the moduli space cannot be irreducible. So that's the first bad news. But it continues. In the supersingular case, one has that h2 of theta is one-dimensional, and in the classical case, it's known that h2 of theta can be 0 or 1. So deformations. So there's a non-trivial obstruction space, and it is known classically that the obstructions are taken. So the moduli space is not smooth. So non-trivial obstructions. I must say, especially in the classical case, this came out as a surprise. This is an unpublished result of Ikedahl and Shepard-Barron from, I think, 2004. Then, good news, there exists a canonical double cover. It's not that of that. Where is it? It's not of this simple form. There's usually a non-trivial extension of OX by omega x, and sort of one can define an algebra structure there. So x tilde to x. So this is finite, flat of degree 2. So this looks like before. This is an integral Gorenstein surface. Integral Gorenstein. It has a dualizing sheaf, which is trivial. And chi of OX is equal to 2. So this is called K3-like. Why don't I write K3? X tilde may be non-normal. And in fact, it's known that after resolution of singularities, several things can happen. Extilde, there are three possibilities. Extilde can simply be a smooth K-free surface. Then it can happen that it is a K-free surface with rational double points, which one could still think of as kind of okay. But it can also happen that the thing has, after normalization and resolution of the singularities, we get a rational surface. So what I'm saying is that sort of the motto now is Enrique's theory is no longer a subset of K-free theory. And because of that, somehow much less is known about Enrique surfaces in characteristic 2. Because we cannot simply use the theory of K-free surfaces.
This construction of Extilde, even in the classical case, is not.
If you do this for the classical Enrique surface, then something horrible happens. Then this is, you get a smooth K-free surface if you start with a singular one. Because what happens is the following. I will come back to this in a second. Pick tau, there is mu2, and then you take the Cartier dual and you get a torsor under Z mod 2, and this is a K-free. But if you start with a classical one, then this is always purely inseparable, and it's never a smooth surface.
So you say your things aren't smooth anyway.
Yeah, but if you, that's also the point that even in the classical case, the cover need not be a K-free surface. However, so the first thing I want to do now is I want to kind of give a structure result what this X tilde really is. And since this is supposed to be something very concrete, I want to talk about projective models. And sort of let me introduce something. I'm not sure, I've learned this from this book of Kosek and Dolgashev, so I don't know whether they invented it or whether this was known before. Maybe somebody in the audience knows. So if X is an Enrique surface and C is an irreducible curve on X, we define the following invariant, phi of C, to be 1/2 of the infimum of the intersection number C dot E, where E is a genus 1 fibration. So let me comment on that. First of all, it's known that in any characteristic, every Enrique surface admits genus 1 fibrations. It's also known that this genus 1 fibration always has a double fiber. So this E is always of the form 2 times some, what people call a half pencil. So because of that, the intersection number C dot E will always be an even number. This is the reason for putting 1/2 here. So I should say the facts are this phi of C is in fact a non-negative integer. And also I should say that phi of C is 0. Well, it is 0 if and only if it intersects one of those genus 1 fibrations 0, so it means it must be contained in a fiber of a genus 1 fibration. Or equal to, contained or equal. Fiber of a. So one could see this phi of C as measuring a little bit of, sort of, these are not the kind of the not so interesting cases, so we can see that if this number is interesting, it will be interesting in case phi of C is positive. And so here I have the following theorem, and maybe I should start on the blackboard. So this is the following result. It's due to Kosek in characteristic not equal to 2, and the extension to characteristic 2 is due to myself. So we have X, an Enrique surface, C, an irreducible curve. Then, if this number happens to be positive, so the kind of, if it's not in a way simply related to a genus 1 fibration, then we can form sort of, so let me remind you for me. So I always have this canonical double cover, x tilde. Then I can look at that. That's now, because I'm working on a singular surface, let me use the language of schemes. So what I want to say is that this is globally generated on x tilde. It's globally generated on x tilde. So we get a morphism from x tilde to, and has to do a little bit of a computation, to 1 plus c squared. So we have this kind of thing here. Let me call this morphism phi of c. So this is in fact a morphism, and I'm claiming that phi is a surface. So for example, if phi of c is bigger or equal to 2, then this is actually not so difficult to see, because then already Ox of c is globally generated on x by classical results on Enrica surfaces. So of course the pullback will be globally generated. And again, if phi of c is bigger or equal to 1, it's classically known that the linear system C on X already defines a morphism or a rational map, whose image is a surface. So of course, I mean, just by looking at a commutative diagram, it's clear that also the image here is a surface. So I don't mind that this is really a highly singular object. So we have this. I write too large. So, yeah, so let me continue with the theorem. So that's the thing to start with. So the second statement is, it's not so interesting, but let me just write it down for completeness. If phi of c is equal to 1, then the degree of this map is equal to 2, and phi c of x turns out to be a surface of minimal degree inside this 1 plus c squared dimensional space. So by a classical result, I think due to Segre, yeah, the image must be a rational surface. So it's a surface of minimal degree, hence it's rational. So it's a rational scroll. I mean, these are explicitly classified. So I should say I'm looking to find, of course I want to find a birational model, or at least, I want to find something that explains me what x tilde is. So in that case, it doesn't tell me that much. So the next thing to look for is to look at what happens if this invariant phi is at least 2. And then it turns out that the degree, first of all, it turns out that c squared has to be 4 at least. This again follows from classical results on Enrica surfaces, to be looked up at Kosak's article or in the book of Kosak-Delgashev. And it turns out that the map phi c is always birational. So this gives us already a first hint where to look for, this gives us a way of getting hands on our x tilde. So how does one prove something like that? It's basically I'm not proving it, I just want to say where my own contribution comes in. So if p is not equal to 2, this is kind of classical techniques on linear systems. So one pulls back the linear system up to the k-free surface, then one looks at potential base points, these kind of the usual games in classical geometry. So the only objection people in the audience might have, well, if you try to do the theorem on x tilde, you run into problems because this is a non-normal surface, so all these notions of base points, should be a little bit should be a little bit careful. So there the following happens, because there are two possibilities. Either the surface is singular, then it turns out that this is in fact étale, and x tilde is k3, and the arguments work as before. It's basically an exercise from kind of an exercise of, in a kind of Hartshorne type, like translating everything in schemes. And in the other cases, this is when x tilde is singular, the following happens. This map pi turns out to be purely inseparable. And so what I can do, I can look at the Frobenius pullback. And so this factors here. And so rather than working with the linear system of the pullback of the linear system up here, I pull it once more further up here. Then I'm again working on a smooth surface. And then, all classical techniques are available. It becomes a little bit messy writing things up, but you can simply rephrase Cossack's proof there. So this gives me a way of completely avoiding working on the singular surface, on this non-smooth surface, because this is purely inseparable. It's a little bit messy, but you can do it. And I hope I've convinced the audience. So what next? That motivates the following. So again, X now an Enrica surface. Sort of the easiest thing I can hope for, of course I want to find birational models of my X tilde which don't have huge codimension or huge degree. So the easiest thing to look for would be phi of c is equal to 2 and c square equal to 4. So we define the following set. Let me call it P, like polarization. So I look at L invertible sheaves on X having the property there exists a curve inside here, an irreducible divisor with self-intersection 4 and phi of c is equal to 2. And I call elements Cossack Werra polarizations. The name Werra will be explained in a second. So this is another very classical result, which actually I stumbled over this article of Werra by pure coincidence, and that kind of inspired the whole research. So I think I should name the name Werra in here. So the proposition now is, if X is an Enriques surface, then there always exists a Cossack Werra polarization. You see, this is different from the theory of K-free surfaces. When we look at K-free surfaces and we look at polarized K-free surfaces, the problem is always that if I fix a polarization degree, I don't capture all of them. But this is kind of different from the situation of well, I have to add something later on. They're not really polarization. Maybe semi-polarizations. L is usually only big at nav, but they're good enough for what I want to do. So, unlike the K-free case, we have always these, and the reason is a very simple one. Namely, every Enriques surface, they have the same Néron-Severi lattice. So it suffices to prove that one Enriques surface has one of those, and so all of them have. So that makes life much easier. But of course, I should say that just to give you an idea, but these are in general not unique. On a complex Enriques surface, this set P of X is usually infinite, but on the other hand, the automorphism group is usually infinite. So, but if X is generic, now generic Enriques over C, then one can, of course, I would like to do it also in the other cases, but I cannot. But this number is in fact finite, and it turns out, just to give you an idea of how far this is away from being unique, so around 250,000, just to give you one idea. It's kind of That will be later on important. Keep that number in mind when it comes to the construction of moduli spaces, because that will be the degree kind of the overparameterizing space I will have. But on the other hand, there exists classical Enrica surfaces in characteristic 2, where even with trivial automorphism group having only one cosec-Vara polarization. And this will later on explain the pathologies Shepard-Barron and Ikeda ran into. So kind of, the number is always non-zero, but it's somewhere in between these extremes. And of course, how do you prove such a thing? As you might guess, this is a lattice theoretical. I mean, you count orbits under of. I mean, well, sort of you have to write down the Enriques lattice. You have to find out one element there. You have to look at the orbit. Sort of, it's not nice. So this is just kind of to give you an idea of how. So we always have such a thing. So now using it, so let X now be an Enrique surface, arbitrary characteristic including 2, then there exists, namely using such a cosec-Vara polarization. So we know already that the map now goes into P5 because C squared will be 4, and the map goes to one projective space of dimension 1 plus C squared. And in fact, the image will be a complete intersection of 3 quadrics. And I should say this result was known in quotation marks already to Enriques. It was definitely known for the generic Enrique surface that there always exists such a map. And then there was and it was kind of vaguely known, probably to experts, that at least over the complex numbers, one always knows that this here, so I should say this is birational. And sort of over the complex numbers, or if this is a K-free surface, then this maps -2 curves onto canonical singularities. So this is really like a nice birational model of the double cover. It's always a complete intersection of 3 quadrics. And I mean, sort of the first rigorous proof of this fact that this is always true, which runs through Horikawa's presentation of special and non-special Enrique surfaces, is due to Vara. And so this is the reason why the name Vara comes into this. Sort of, this is implicitly, one could also Vara phrases that there exist these kind of polarizations. So and so this is my reason for calling them cosec-Vara polarizations. And so sort of the thing here is that this is in fact even true in characteristic 2. And somehow, why is that true? We know already that that we have a birational map to projective 5 space, and so the thing to do is to is to prove that this is a complete intersection of 3 quadrics. So the idea is as follows, and now it's really getting technical. You have to convince yourself, using appropriate versions of the Bertini theorem, that a generic hyperplane section cuts out on X tilde an integral Gorenstein divisor. Why is that true? X tilde is Gorenstein, so simply pullback of a generic hyperplane section will be a Cohen-Macaulay curve in particular. I mean, it's given by regular sequence, so Gorenstein. Then by appropriate versions of Bertini, it's still true, even though that may be highly singular, that this generic hyperplane section is an integral Gorenstein curve. And then one plays these usual games that, so I take P and so L is now a cosec-Vara polarization. I take here a generic divisor. And then one studies these kind of on X tilde. I mean, this is Cartier divisor, so I can still write down something like that. And then from a junction, which also holds in this setting, we have something like that, then one has to control the cohomology of these sheaves, which is no problem because then you push them down, use appropriate vanishing results on Enrica surfaces to show that taking cohomology, this is always a surjection, and that gives you take the canonical ring here, and this surjects onto the canonical ring of D. Well, so if D, if X tilde was a smooth K-free, a smooth K-free surface, then D would be a smooth divisor, and by the Noether-Enriques-Petri theorem, we would know that except for special cases that can be ruled out easily in this case, that this ring here is generated in degree 1 with relations in degree 2 only. And using an appropriate lifting trick, that would give generation of degree 1 and relations in degree 2 here as well. So what we need is a version of this Noether-Enriques-Petri theorem for highly singular curves. Unfortunately, this has been established by Schreier. And so basically, kind of the classical arguments with hard work can be made. So then, sort of Noether-Enriques-Petri, kind of for singular curves due to Schreier, give that plus a little bit, that this is generated in degree 1. Relations only in degree 2. Then one can show, one has to exclude that D is a hyperelliptic or a trigonal curve, or, this is this kind of classical result. Then, this is kind of easy. Well, it's comparatively easy. And then kind of lifting appropriately, one gets the result up here. And then kind of the same. For this ring, but that means that this ring that the embedding with respect to the linear system D is projectively normal and the image is cut out by quadrics. So the map phi projectively normal cut out by quadrics. Well, and then you simply count quadrics and you find out that there are 3, but the codimension is 3, so it must be a complete intersection. So this gives you, and so this tells us what this K-free-like cover is in any case. It is always birational to the complete intersection of 3 quadrics. And this is something, of course, which has a nice deformation theory and which has a nice... So now we really start to get our hands on Enrica surfaces also in characteristic 2. So in fact, this what I'm doing now is kind of now works in any characteristic, but kind of especially... in the end, everything can be done over the integers. So now I can start constructing moduli spaces. So we start again now with an Enrica surface and we choose one of those cosec-Vera polarizations. Then sort of now I'm looking at the proj of this graded ring. So this is, we now know that this is our complete intersection of three quadrics in P5. So nu is birational. And kind of if X was a smooth K3, then this simply contracts -2 curves. So proposition, a little bit technical, that if R is a complete local Noetherian with ring with residue field K, and X is a formal deformation, then there are two cases. So if X is classical, or characteristic is not equal to 2, then L, sort of, now let me say, maybe L is not a good idea. M an invertible sheaf, any invertible sheaf on X, then M extends over the formal deformation. This is clear because in the classical case, H1OX and H2OX vanish, so there are no obstructions. But now the interesting case is, in the other cases, X non-classical, then the deformations of M may be obstructed, but M squared always extends over the full formal deformation. So in particular, we can choose an ample polarization, an ample line bundle on the special fiber. It will always extend, and that implies that every formal deformation of Enrica surfaces is effective. So this is kind of the key point to construct moduli spaces. In particular, formal deformations are effective. I should say, this of course is a highly here work is required. Somehow the idea is, what I can show is that if you simply look at successive extensions, one can show that these are related to the first and second cohomology group of the de Rham width well, in that case it's just W of omega. And this is always two torsion, no matter how complicated it is. And this is kind of the reason behind that. So in a certain sense, yeah. So, but that's a kind of rather technical result. Unfortunately, this is like kind of the technical heart of the whole thing, and also under the same hypothesis. This is again something which is technical but kind of believable. If I look at the pic tau, that is the torsion component of the Picard scheme in a family, this is always a finite flat group scheme of length length 2 over R. Is finite flat of length 2 over R. So kind of, it's clear, this is a classical result of Bombieri and Mumford, that this is true for Enrique surfaces over the over a field, but I need this in families. And it's kind of what could happen is that the thing blows up or something strange happens. It does not. And kind of you need that but then it's kind of not so difficult to see. First of all, because every formal deformation is in fact effective and without loss of generality projective, there are very strong results on how on representability of pic tau. So very horrible things cannot happen because things are projective after all. And let me see, what was the other argument? Well, and then again, unfortunately, one has to split up in the classical, non-classical case. Sort of it's so. So why does this help? So, yeah. So we now fix again X and Enriques and the Cossack-Vera polarization. So Enriques, Cossack-Vera. And so I have X over, say, SPF Well, no. Now we know everything is effective. Assume a deformation of X. Assume L itself extends over R. We will see in a minute that this is actually... I won't spoil it. Then, so we know that this is a finite flat group scheme. Then we can form this 2-to-1 cover. So if I have a finite flat group scheme of degree 2, then this implies that there exists a peak, there is a torsor under the Cartier dual. So this is a result, I think it's due to Renault. So this is a torsor. So in case, for example, if we're in characteristic different from 2, this simply means that this group here will be Z modulo 2Z. The Cartier dual is non-canonically isomorphic to Z modulo 2Z. And so saying that this is a Z mod 2Z torsor simply says it's a finite étale cover, a Galois cover with group Z mod 2. But this is kind of more complicated in the other cases. And so, of course, since L extends to the whole family, we can use, of course, this will define as a map to P5 of R. And since the special fiber is a complete intersection of 3 quadrics, well, this small deformation here will be. So there is no problem here. So this is again image a complete. Well, let me say simply 2 complete intersection. And since I was told before the talk that this is an explicit talk, I now have to do something explicit. So it looks a little bit technical at the moment, but it is much simpler than one might actually think. Namely, by Tate and Oort, such group schemes over local Noetherian bases are classified. One knows that our pic tau must be of the form, it's called G sub A and B. And this is by definition, so I have to tell you what it is on points. So this is something which is the set of all S. S squared is equal to AS. And there exists even something which one should call the regular representation of that. And one can work that out in terms of matrices. And with an appropriate basis, I get. So. And somehow, let me tell you the invariant quadrics. Sort of let me think of this as kind of a vector space. Kind of this acts, of course, on the polynomial ring variables, on, say, x and y. And I can ask what are the invariant quadrics. This is kind of a r x, y, y squared minus axy. Oh, I should also say that a times b must be equal to 2. So my point is that things can be made really explicit. And so now on P5, R, I choose coordinates or there exist the coordinates x1, x2, x3, y1, y2, y3, such that the action, here of course we have this pic tau d acting. It's not very difficult. This acts of course on all these vector spaces here, inducing an action of the same group scheme on this ambient P5. And it turns out that such that kind of pic tau d acts on P5 via this regular representation, 3 copies, kind of xy, 1y, x2, y2. Why is that true? This is kind of yes? Pardon? I need the m several times. So this m here in the proposition, m is just an arbitrary invertible sheaf. And if I choose this sheaf to be ample, it implies, this extension implies that every formal deformation is effective. And somehow, this is an ingredient which I will need later on here. At that moment, I'm assuming that I have a deformation and this L extends, because a priori I only know that L tensor L might extend. And L tensor L is a little bit too ample for me.
And in this next proposition, you're just saying that big tau is finite by the length 2. You don't know anything about this big variation. That's what you're doing right now.
Yes, sort of I know it's finite flat of length 2, and somehow what I'm saying is, so where I want to go to is that every deformation of x defines me a deformation of the pic tau, and somehow this will give me later on a morphism from the moduli space of Enriques to this kind of deformation space of, which will, it will explain later on why it's important. So here I'm just trying to tell you, I'm starting now with a deformation, maybe just with x itself. I take the double cover. I can find coordinates in such a way that the group acts like in this particular way. There exists A and B. I don't know what A and B is. I only know by the abstractly there exists A and B such that A times B is equal to 2. The action is like that. Somehow I want to show that...
Sorry, one other thing.
Yes?
You're not saying that big tau is connected, right?
No, I'm not saying that.
So why did you dualize?
Because this is a general fact that if you have a subgroup scheme inside your pic, then it gives rise to via the Cartier dual. Usually, people in characteristic 0 go over that because there is a non-canonical isomorphism. And so, using this now, we kind of sort of the first thing I note is that now proposition that phi, so this is now this phi here, of x tilde is a complete intersection not only of 3 pic tau d invariant quadrics, which tells me, once I know that, I know precisely that I can really start down. I have now really hands on the situation. I know that my x tilde, or the image under this map here, is in fact a complete intersection of 3 quadrics, and I know that these quadrics come from this kind of vector space. I've given you up there a basis. It's like, so it's from this vector space xi, yi, y squared minus blah, blah, blah. So I really have now I know how the quadrics look like. I know there are 3 of them, linear of those. And so this is the image of my x tilde. And so somehow what I want to say is that if x is Enriques, with at worst, now I'm allowing Duval singularities, canonical singularities, because I can sort of, this here has Duval singularities, and this here has the property that OX of 1 will be ample, just by construction. L, an ample cosec Vera. So it's a little bit like in the case of varieties of general type. I pass from the variety to its canonical model. So I'm starting off with an Enrique surface and a Cossack-Vera polarization. I do this contraction map, and I end up with a surface that has at worst canonical singularities, but now L will not only be ample, but in fact very ample. And then this will be in fact the X tilde of this, the canonical double cover of that, will be in fact not only birational, but it will be a complete intersection of three quadrics. And then I'm saying, then if I'm looking at deformations of the pair X, L, and I'm looking to the deformations of group schemes of length 2 by simply associating to every X over L the pic tau, then I claim that this functor is smooth. Why is that? Sorry for being a little bit technical now, but kind of the reason is that we have our X over spec K. We have our deformation R. And the question is we want to extend this over some infinitesimal one. But then what's happening? Now I have this extremely explicit description over there. I know that without loss of generality, everything takes place inside some P5. And once I know that the group scheme pic tau extends from here to here, I can use this upstairs and this description of the invariant quadrics by simply writing down an extension of this double cover. Well, actually, I should. No, sorry. I need a little bit space above. So I'm saying that this here now takes place in P5. And if I extend this now, so this is a small extension, then I can simply, if I can extend the group scheme, I can extend the action on P5 by simply by extending I know the action on P5 is simply it acts via 3 copies of the regular representation. So if the group scheme extends, then clearly the regular representation extends. The invariant quadrics, from the explicit description there, it's kind of clear that you can extend them because you only have to lift A and B accordingly. So that tells you that I can always find an extension here. And then a descent argument tells me that I can always find something here. And that tells me that the only way this cannot extend here is that the group scheme does not extend. But that's precisely the statement. So this functor is smooth. And so now,
sorry, just a very silly question. I should have paid attention. Where did the quadrics come from?
I'm simply saying I know I have an action of the. I have the quadrics come from the following. I take the polynomial ring in 2 variables, and I let G act via that.
Right.
And then I'm asking which quadrics are invariant under this action. And this is a question, I don't say it's, well, you can do this. And then I'm saying a little bit of a representation theoretic argument tells me that in fact the image of the canonical double cover is not only invariant under the quadric, but it's a complete intersection of 3 quadrics, each of which is invariant. And this gives me now, where do I have the... And now this gives me already the first 5 minutes left result. So how we now study, we can now already study the lifting problem for Enrique surfaces. Namely, if X is an Enriques with, at worst, Duval singularities, admitting an ample cosec-Vera polarization. We know every smooth Enriques admits a cosec-Vera, and I can contract it. So this, up to resolution of singularities, this applies for every Enriques surface. Then, if X not supersingular, then it implies that X lifts over the Witt ring. Why? Because if X is not supersingular, it turns out that the pic tau is not alpha 2, and it's known that these group schemes lift over the Witt ring. That gives me a formal lifting over the Witt ring, but then using the, I think I wiped it out already, the result on the extension of ample line bundles gives me algebraization. So we have lifting over W2, and if X is supersingular, the only thing which is important is that I have to see how I can lift alpha 2, and it is known that alpha 2 lifts if I adjoin the square root of 2. So this completely settles the lifting problem for Enrique surface in this case. And then there is, for example, a result by Artin on simultaneous resolution of singularities. So if you prefer to work with smooth surfaces, at least that tells me that Enrique surfaces lift in any case to characteristic 0. Although after resolution of singularities, I may lose control over the ramification degree. So that gives me lifting. And although let me finally describe the moduli space. So we define the following moduli space, namely we look at X Enriques with adverse Duval singularities, L an ample cosec-Vera polarization. Then from here, using the effectivity results and the deformation results, it's kind of, and the explicit overparameterization using the invariant quadrics is a quasi-separated Artin stack of finite type over, let's stick to fields. In fact, it's true over the integers. And sort of if, let's say, P characteristic of K, then if the characteristic is not equal to 2, then it's irreducible, unirational, smooth, and 10-dimensional. This is now easy. Irreducibility and unirationality follows from the fact that it's basically a quotient of this space of invariant quadrics by an appropriate group action. So this gives me irreducibility and unirationality. Smoothness follows because in characteristic not equal to 2, h2 of theta is 0. 10-dimensional follows because h1 of theta is 10. So that's kind of, I'm not sure whether this was known before. It was definitely known over the complex numbers, but I get it kind of for free here as well. Kind of the really interesting case is characteristic 2. Here, the space has two irreducible components. We already know it cannot be irreducible. So it has two irreducible components. 10-dimensional, intersecting transversally. At a 9-dimensional space, a substack, And somehow, so this is the picture. And it's like one component corresponds to the singular Enriques. One is the classical. And as you may guess, the intersection is precisely the supersingular locus. And so this is where the moduli space is very nice. And since I'm already over the time, there is one issue here, which is, I don't have the time to say anything about it, but it's in the paper. One may object, I mean, this moduli space is really nice. But then there are these examples of Shepard-Barron and Ekedal that tell us that the moduli space of Enrica surfaces, even on the classical component, is obstructed and attains hypersurface singularities. So when I first saw this, I thought I had made a mistake in my results. The problem is, it's a phenomenon which is known from moduli of canonical models of varieties. Namely, there are two moduli spaces for say, canonical kind of varieties of general type. There is the one, for example, for surfaces, there is the one parametrizing smooth minimal models, and there is the one parametrizing canonical models. And if one does simultaneous resolutions, it can happen that on that way, the moduli space picks up singularities. So there are, for example, examples by Catanese over the complex numbers showing that the moduli space of canonical models of surfaces of general type may be even very nice, but then after a kind of one passing to the one of the minimal models, one gets everywhere non-reduced moduli spaces. And this is somehow similar what happens here. There are these very, very special classical Enrica surfaces here, which admit only one cosec-Vara polarization. And it turns out, if you do the analysis, that then the canonical double cover is non-normal, and then part of the non-normal locus gets contracted under the map to P5. And when one looks at such points here, when passing to the simultaneous resolution, this is what we have to do when constructing the moduli space of Enriquez surfaces. The moduli space of Enriquez surfaces in characteristic 2 picks up singularities. So in a certain sense, my motto would be the moduli space of Enriquez surfaces in characteristic 2 is kind of the wrong one. This is the right object. And I think I'll stop here.
Any question or comment?
Yeah, can you start the moduli over spec Z?
Yes. It's again a quasi-separated Artin stack of finite type over spec Z, and in fact it's smooth over Z x y minus 2, and this comes precisely from the fact that the pig tau, the finite fat group scheme, has, this is the deformation space for that. Yeah. I think, I didn't check it. It should be the linear Mumford for P not equal to 2, but it's definitely not a linear Mumford stack for P equals to 2. Because, here's the reason. There are some surfaces here where H0 of theta is 1, and nearby surfaces where it is 0. This shouldn't happen for a dilinear Mumford stack. This cannot happen for a dilinear Mumford. It's always out in. I'm not sure, maybe with lots of works I could maybe get away with this, but I'm not sure, because this quasi-separated issue is something which is all over the place when working with simultaneous resolutions, and it might be hard work, and in the end it might not be true. So. Well, I would say, I didn't study that, but there is a natural candidate. You simply take, the complete intersection of 3 quadrics. This space has a natural compactification, but I'm not sure. I assume there are horrible things in the boundary. So I'm not sure.
Any further question? Okay, let's thank the speaker again. We'll have a banquet.